Now, I strongly suspect this video is redundant with another one I've already made, because I think I've gone over this, except I don't remember seeing the aardvark on the screen. And you can tell that's not my picture of the aardvark, that's somebody else's, because the art is so much better than mine. Well, to the transformation. Okay, we have a transformation that's based on the vectors 1, 2, and -1, 3. Okay, and these vectors are going to be eigenvectors of our transformation. Now, in the basis that consists of these two vectors, the transformation is going to be represented by this matrix. And the effect of this matrix, as you can easily verify, if we multiply this by the vector 1, 0 in our basis, and you know, my B for the basis needs to be a lot fancier, so let's go ahead and make it look incomprehensible. Okay. Okay, our vector 1, 2 expressed relative to this basis is just 1 times this plus none times this. That's the vector 1, 0 relative excuse me, to this basis. And our vector v2 is 0, 1 relative to this basis. It is the vector -1, 3, but expressed relative to this basis, it's none of this plus 1 of this. And that's a unique representation. Each of these representations is unique. There's only one way to represent this vector relative to this basis, and this is it. There's only one way to represent this relative to the basis, and this is it. Okay? Now, relative to this basis, what we want to do, well, ultimately what we want to do is we want to triple this vector and then multiply this one by -2. Now that's going to have the effect of tripling this, which is going to give us this vector. That's our transformation of the vector 1, 2. It's going to be 3 times the 1, 2 vector, giving us the 3, 6 vector. And this is these unsubscripted vectors, okay, column matrices, are the actual representation in R2. Okay, these are the actual coordinates in R2. These are not actual coordinates in R2. These are coordinates, again, relative to this basis. Okay, so if we triple this vector, what are we going to get? We're going to get, well, 3, 6. Triple this, we get the vector 3, 6. If we multiply this vector by -2, we're going to double its magnitude, giving us a vector of doubled magnitude. And since we multiplied by negative, we're also going to reverse its direction. So our transformation on the vector -1, 3 is going to be going to give us -2 times the -1, 3, or the 2, -6 vector. Okay, again now, relative to the basis that consists of those two vectors, all we have to do is multiply the vector 1, 0 by the matrix 3, 0, 0, -2, and the vector 0, 1 by the same matrix, and we're going to get exactly the same result, but it's not going to look like it. What we're going to get if we multiply this by our v1 vector, which is 1, 0 in this basis, we're going to get 3 times 1, 0, or 3, 0. Of course, what does 3, 0 mean? 3, 0 means 3 times the first basis vector plus 0 times the second. Well, 3 times this is 3, 6. 0 times this is 0. We again get 3, 6. In other words, the actual R2 vector will still be 3, 6, but relative to this basis, it's 3, 0. And then if we multiply the matrix by this vector relative, the vector v2 relative to our basis, we're going to get 0, -2, meaning 0 of these and -2 of these. But -2 of these is, of course, just this, as you can easily verify by multiplying. So I write all that out. I say our transformation of v1 relative to the eigenvector basis, relative to our basis consisting of v1 and v2, we multiply the matrix by the 1, 0 vector both relative to the eigenvector basis, or both relative to this basis, which is, because of the matrix, going to be our eigenvector basis. And we get 3 times the 1, 0 vector, or the 3, 0 vector relative to this basis. And as I just said, that means 3 times the first vector plus 0 times the second. Well, here's 3 times the first vector and 0 times the second. And that gives us 3, 6. Okay, then TV2, V2 relative to the eigenvector basis is just none of these, one of these, 0, 1 relative to this basis, and gives us this, and that should be fairly easy to understand. Now, of course, you have to work out the details. Go back and think about what everything means, and think about how well you know everything we've done in the course up to this point as well. You might have to review some other things to completely understand this. Hopefully you're up to par on all those things. Okay, well, I was going to say something, and I don't read from a script, so sometimes the brain gets diverted. Yeah, the thing that makes this the eigenvector basis is not automatically the eigenvector basis, but as soon as I multiply in relative to this basis by any diagonal vector, it is an eigenvector basis. Okay, so I can say that diagonal matrix occurs, double implication sign, if and only if your basis consists of the eigenvectors. Now this is really a big deal. Okay, you'll see why. You'll see some of why in the fairly near future. It goes much deeper than anything we can do within the scope of this course. But the diagonal matrix means that whatever your basis is, it's an eigenvector basis. So with respect to this basis then, if the matrix is diagonal, that makes these eigenvectors. And again, you can see, if I multiply by this matrix, that means that this is an eigenvector. Okay, that we're going to get 3 times this basis vector, and ultimately that's what we get. And similarly with this, we're going to get -2 times this vector.